Welcome to another session of Everyday Mathematics. Here at Everyday Mathematics, we say that we do enjoy solving the harder problems, but also we see and appreciate the beauty in the simpler problems. So I saved the most beautiful problem in the MIT 2022 integration B season. I saved the last problem as regards trigonometry for this last session on trigonometry. And this comes from the MIT 2022 integration B quarterfinal. Number 3, problem 3. So the problem is limit of n tending to infinity of the product of n and the integration of sine of 1 over x to the power n from x is equals to 0 to x equals to infinity. So very beautiful problem. Now, before I jump onto the solution, I'd like to thank our subscribers. We thank you so much. Thank you for entrusting us with the support. We don't take it for granted. We really treat it so dearly. Now, for our first-time visitors, we do encourage you to subscribe to our channel here at Everyday Mathematics. We do enjoy solving, looking at the very hard problems. And if you're one of those who enjoys just looking at harder problems and looking at solutions, we are that place that you could stop to cure your curiosity. Now, for our friends who are here for a second, third, or fourth time but haven't yet decided on whether to subscribe, we do encourage you to subscribe to our channel. We'd use your support because that extra visibility what your support gives us will come in really handy. Thank you. Now let's jump into the solution. So the limit of n tending to infinity of the product of n and the integration of sine of 1 over x to the power n from x equals to 0 to infinity is the problem. The first thing I'll do is let u be equal to 1 over x to the power n, such that when we differentiate u with respect to x, we get negative of n over x to the power n plus 1. Now, du dx now is negative n over, since we have a product of x to the power n and x. The x to the power n is the same as 1 over u. And the x here is the same as the nth root of 1 over u. So we can now take that so that du dx is negative n over 1 over u, and the nth root is expressed as 1 over n. So we have the product of 1 over u and 1 over u to the power 1 over n. So that when we multiply both sides with the denominator here and dividing both sides by the numerator, we get that 1 over u times 1 over u to the power 1 over n negative over n du is equals to dx. So substituting for dx and for 1 over xn in the original equation, we get limit of n tending to infinity of n. Now, since we did substitute u being equal to 1 over x to the power n, when x tends to 0, therefore x tends to u tends to infinity. So the lower limit tends to infinity, and here as x tends to infinity, u tends to 0. So the upper limit tends to 0. So that's why we have a reversal of limits here. But now, under the integral sign, we have sine u, u in place of 1 over x to the power n, and then in place of dx, we have what we have here, which is negative of 1 over u times 1 over u to the power 1 over n du. So we can see here that this n and this n here would cancel out, and so we are left with the limit of 1 over u over u to the power 1 over n sine u over u. Now, because of this negative sign, we can now flip back the limit so that now 0 is the lower limit and the upper limit is infinity, and the negative sign disappears. So the important thing to see here is that the limit of 1 over u to the power 1 over n which can be expressed as u to the power negative 1 over n, as n tends to infinity, is u to the power 0, and that limit is the same as 1. So this first term here tends to 1, and so we remain with the integration of sine u over u from 0 to infinity. Okay, now how do we solve this integration? I think we can use the technique that we covered previously in one of our problems, and that is a technique that was popularized by RIchard Feynman, and that is the technique of differentiation under the integration sign, or in the lingo of mathematics, using Leibniz theorem. And so what we would do there is we would say let IA be equal to the product of e to the power negative AU times sine u over u. And there's a reason why we've introduced this term, such that this initial integration is I to the, in bracket, infinity, or is the same as this integral as a tends to infinity. So as n tends to infinity, this initial term tends to this integration here is the same as I 0, so that this first term tends to 1 when a tends to 0. So we have the integration of sine u over u from 0 to infinity. Now, when we take the derivative of IA with respect to a, we get we differentiate, or we get the partial derivative of e to the power negative AU, and that is the same as negative u times e to the power negative AU times sine u over u. So the u's cancel out. Now we do have a negative here. So we're going to use now integration by parts to try and solve this equation, right? So we have that. The first term there is e to the power negative. So we take this as a product of u and dv. And with dv, we consider negative sine u as our dv, such that v is cosine u. Because when you differentiate cosine u, you get negative sine u. And then u is e to the power negative AU. So the product of uv is e to the power negative AU, e to the power negative AU cosine u with limit 0 and infinity, minus the derivative du. Du is definitely looking at this, is negative a e to the power negative AU. So essentially, and then we have cosine remaining there. So when we introduce the limits there, we have a to the power negative AU cosine u with the limits there, so that at when u is infinity, or when u tends to infinity, this initial term goes to 0. So that is 0 minus, when u tends to 0, we have 1, and then cosine u is 1. So we have negative 1 there. Negative 1. And here in brackets, we have a 0. Plus, again, we have another level of integration by parts. So we have a times e to the power negative AU sine u du. So this part here is very similar to the IA dA. So when we simplify our differentiation, we get negative 1 minus a squared times the integral of from u is equal to 0 to u is equal to infinity of e to the power negative AU times sine u. So this here is the same as this here. So we can take this component to the left-hand side. And so we have dIA dA plus dIA dA is equals to -1 minus a squared dIA dA. So collecting like terms, on the left-hand side, we're left with -1 on the right-hand side. And so dIA dA is equals to -1 over 1 plus a squared. So what is IA? IA is the integration of -1 over 1 plus a squared. And so how would you solve that? Is by letting a equals to tan theta, and dA d theta is sec squared theta, and dA is sec squared theta d theta, and therefore I theta is equals to -1 over 1 plus tan squared theta times sec squared theta. And so I theta is equals to negative sec squared theta over sec squared theta. And that is the negative integration of d theta, which is negative theta plus c. And since we said a is equals to tan theta, therefore theta is the arctangent of a, and therefore IA is equals to arctangent of a plus c. So our IA is essentially negative arctangent of a plus c. And how we could try to solve for the constant c, as a tends to infinity, IA is equals to the limit of a tending to infinity of arctangent of a plus c. And when we plug that limit in the original integration, the entire integration goes to 0 because e to the power negative au when a tends to infinity is 0. And therefore, that means is that arctangent of a with a tending to infinity is negative, of negative tangent a is negative pi over 2, and c is c, but then the integration goes to 0. So essentially, c is equals to pi over 2. Therefore, what that means is IA is equals to the arctangent of a plus c. Now, our original integration is the integration of sine u over u from 0 to infinity, and that's the same as I0. So our answer is the arctangent of 0 plus pi over 2, and therefore, which is 0, arctangent of 0 is 0 plus pi over 2. And this is our final answer. This is our final answer, which was very, very interesting problem. Thank you so much for hanging around with us. It was fun and really a pleasure solving this problem with you. Thank you. Until next time. Bye-bye.